This week we're gonna talk about fractions. So I want to focus on the common fractions misconceptions that students can have and how we can address those common misconceptions. Okay, and these four things are the most common misconceptions that students have shown in the paper, in the research. First one is not understanding the denominator. Second misconception is why is 1/4 smaller than 1/2? The third misconception is the language of fractions. And the fourth misconception is which numbers are added or subtracted. Understanding fractions is essential to understanding math in general, but common misconceptions can leave both teachers and students feeling more unsure than they should, right? So we know that it is true that we may not notice misconceptions in every primary math lessons or with every student. Knowing what common misconceptions look like and how to address them can make a significant difference in your learners' understanding. So let's look at some common misconceptions in fractions and how the very early ideas about fractions are essential in forming firm foundations. The first misconception we're going to talk about is not understanding the denominator. If they have a firm understanding of the denominator, they will reduce their misconception about fractions so much more. So what does a denominator mean? It means that which names in Latin. So that translation identifies the denominator is a name, just like 1, 2, and 3 are the names, right? So we're gonna say how many halves are there, how many thirds are there, right? Things like that. Or you can think about the denominator can also tell you the size of the parts from the one whole. So in one whole, how many halves are there? In one whole, how many thirds are there? How many fourths there are? Things like that, right? Understanding the denominator, students will have less misconceptions about it, right? They will understand fraction a little bit easier. So some students think this part of boy's picture here in rectangle and one in the triangle are not the same size. But we all know that it's the same size. How do we know? You can think about the meaning of the denominator, right? We could put this piece. Well, we first maybe can cut these two out and compare the wholes. So this square and that square could be the same size. Cut them together, cut them out and put them on top of each other and see the sizes are exactly the same. Or we can use the rulers to measure, the length and width and see it's exactly the same size. So we know that it is exactly same whole, W-H-O-L-E, right? And then we can cut these two out, or we can just fold them and see that these part of the boy's picture and the girl's picture are exactly the same. So this rectangle and that rectangle is exactly the same. What does that tell us? That means we have only one half right here and another half here. We can do the same thing here. If we fold this on this line, it's gonna be exactly the same size. What does it tell us? We know that this square is halved, right? So it's cut in halves. So this is 1/2 of this one whole square, and the girl's picture is also 1/2 of the square. Thus, we can conclude that this rectangle and this triangle both are the same size as 1/2. Same for the girl's picture in the rectangle and in the triangle. So we can use physical paper pieces to show that, right? So I encourage you to give your students opportunity to discover, this using some physical materials first and develop the language associated with the idea. Okay, so here are some more examples. Using exactly same size of a rectangle, we can always show different fourths. So this is the easiest way to make 1/4. This part is 1/4, and that part is also 1/4, 2/4, 3/4, 4/4. That makes one whole, right? That's also same here. These two are equal, these two are equal, and these two are also equal, these two are also equal. So we know that each of these pieces is 1/4 of this rectangle. So what can we say? We know that this is 1/4, same as here. That's 1/4, and that's the same size, 1/4. And this triangle is also 1/4, and that triangle is also 1/4. So even if we have, these different shapes of rectangle or triangle or long rectangle, shorter rectangle, they are all 1/4, same sizes. Okay. So if we concentrate on the size of the pieces and understand that each size has a name as 1/4, or in this case, a quarter, the notation becomes so much easier to understand, right? Okay, then I'm going to introduce you the unit fraction. Why is the unit fraction important? Because that's just like a name or just a unit. When we are counting, we are saying that, how many what? How many pencils? How many meters? How many, or whatever the unit you are using, right? We are measuring or counting by the units. We need to find that out, what we are counting. That's exactly the same thing. So going back here, we can say that this is one piece of what? One piece of 1/4. So one piece of one whole thing out of 4 pieces, right? So we can call this one part as a unit fraction. In this case, it's 1/4. So we can count how many 1/4 are there. 1/4, 2 1/4, 3 1/4, 4 1/4. So if we eliminate this part, we have only 3 pieces of 1/4. So 3 1/4, which is 3/4. Including that together, we have 4 1/4. That makes one whole. Okay, so we will do a little bit more unit fraction here. So if we are looking at that green triangle in this hexagon, we're gonna see how many triangles we can make in this hexagon. We can say here's 1, 2, 3, 4, 5, 6 as total. They are exactly the same sizes. They are all 6 equilateral triangles that makes this hexagon. And this green part shows 1/6. That is the unit fraction, and we are counting how many these triangles can go in this hexagon. We know that 1, 2, 3, 4, 5, 6. Sixth. 6/6 makes one whole hexagon. Okay, so if I ask you a question like, can you represent this yellow part of the hexagon in fraction? How would you say that? We are counting how many sixths there is. So we're gonna count by sixth. 1 1/6, 2 1/6, 3 1/6, 4 1/6, 5/16. So this yellow part count 1, 2, 3, 4, 5, 1/6. 5/16 or 5/6. So yellow part is 5/6. We counted by the sixth. So the unit here is 1/6. We call that as a unit fraction. Let's look at a little bit more. So this is easy. We know this is 1/2, right? Yellow part. Let's look at only the shaded part. That's 1/2. How many 1/2s are shaded? Only one part, right? So we just called it as 1/2. Let's look at this blue. We are making 1, 2, 3, 4 equal parts. And in each part, we know that that's how many, that's our unit fraction. So 1/4 is our unit fraction, and we are counting how many 1/4 there are shaded. 1, 2. So 2/4 are shaded. Same for this one. We made this circle into 3 equal parts. So our unit fraction becomes 1/3. How many are shaded? How many thirds are shaded? We count 1, 2 thirds are shaded. We call that 1, 2 thirds. 2 thirds. Does it make sense? I hope so. And we see that here, 6 equal parts are in one whole. So we know one section, only one part is the unit. Because we have 6 equal parts, this one part will be 1/6. That is the unit fraction. How many are shaded? How many 1/6 are shaded? 1, 2, 3, 4, 6 are shaded. So we call that 4/6. And so on and so on. Okay. So if I just ask you to find what's the unit fraction in this row, 1/3 is the unit fraction. 1/6 is the unit fraction. 1/8 is the unit fraction. 1/4 is the unit fraction. Why is it important? Because then it's gonna be so much easier to do some addition and subtraction. For example, if we are adding 1/6 and 2/6 together, we can just count how many 6 are there. 1. How many 6 are here? 2. Oh, they are same units, so we can just add them together. 1 and 2 6 are there all together, so we can just add 36. So instead of you telling them, well, when the denominators are equal, you can just add the numerator, you don't have to do that. Students can understand more because they know that they're counting how many 6 there are. For subtraction, the same thing. You have 5/7. Now you are taking away 1/7. Hey, we are counting by sevenths, same unit. How many 7ths are left? Now, we know that we had 5 and 1 part of 7th is gone, so there are only 4/7. So counting by the unit fraction, it becomes so much easier. Then we can also think about when your denominators are different, what would you do? For example, 3/5 minus 1/2. We know that we cannot just subtract 1 from 3 because our units are different. When you have a different unit, what do? We need to make the unit the same. That's why we are changing the denominator the same, because that is the unit fraction. So how do we change it? Well, you can think about least common denominator. So you multiply this by 2, then what's the equivalent fraction? This is a little bit different story. I'm just focusing on the unit fraction here. So I'm not gonna do whole procedure in the thinking behind why we are doing the least common denominator here. But we all know that we can find least common multiple and equivalent fraction in this way, right? And we can just explain, now we have same units and it is still equal because 3/5 and 6/10 are equivalent fraction. You can explain with the physical representations too, right? And 1/2 is the same as 5/10. Now we can take away 5 from 6 because both are counted as the 10th. We have the same unit fraction there. So how many tenths are left? Oh, only 1/10 is left. You can do this because it's the same unit, right? So here are some standards from Common Core state standards. Maybe your school has adopted a Common Core, maybe your school didn't. If your school didn't, maybe you have state standards that have adopted it too. Take a look at the standards, the content for fourth graders. If they are talking about unit fractions there, Common Core does have the unit fraction parts. Actually, it has a lot. So here are some of the standards about the unit fractions. For example, content standard for fourth graders in number and operations about fractions. The third one is understanding a fraction a over b with a is greater than 1 as a sum of fractions 1/5. What does it mean? We are counting how many b's using the 1/5 as the unit fraction, and we are counting the sum of fraction 1/5, which means how many b's there are as a total. There are a many b's, right? So a over b means there are a many b's. So one whole is broken into b equal pieces, b many equal pieces, and there are only a many as a whole. So here are some more unit fractions that you're gonna take a look at. I will just take a look at one more. I want you guys to have some time to read all of this carefully, okay, by looking at whether you're pausing this video or by looking at the notes. Okay, so second one here I have is understand addition and subtraction of fractions as joining and separating parts referring to the same whole, right? So with the same whole, and you have addition and subtraction as joining and separating parts when you have the same unit fractions. Okay, so things like that. Okay, second common misconception is why is 1/4 smaller than 1/2? Students learn that 4 is greater than 2 by using what? Maybe some manipulatives, right? Showing 4 apples, that's more than 2 apples. And we know it is true. So knowing that, does that tell us that 1/4 is also greater than 1/2? So here I'm gonna show you some manipulatives. For example, let's suppose this is the chocolate bar and this is one whole thing. Okay, so to show 1/2, we can break this into 2 equal parts, right? And we can do the same thing here. Let's have another one exactly the same size of the chocolate bar, but this time we are making this into the 4 equal parts. So to represent 1/2, we have only 1 part out of 2. And in this chocolate bar, to show 1/4, we have only 1 part out of 4 equal parts. Which one's more? Which one is greater? Now students can see that, oh, this 1/2 means only 1 part when you break that into halves, right? Two equal parts, which one's bigger? This is bigger than 1/4, of course. So you can actually cut out the paper or fold it, or use cookies or chocolate bars, whatever the physical materials you can have, right? Another example that you can think about is like you have $1 or $100. Maybe $1 should be okay. If you have $1 and you are giving that to 2 people, including your student and your student's friend, how much would your student get? You can ask your student and they will say 50 cents. Is that more, or by dividing that by 4 people and you get 1 part out of that? And they will say, oh, if we have 4 people there, we're gonna get 25 cents per person compared to 50 cents when we shared $1 by 2 people. So they can see that the more people they are sharing, the less money they're gonna get. So some examples like that, using the real world situation, they can have some sense that if your numerators are the same, when your denominators are smaller, that number is actually, the denominator is smaller, then that number is actually bigger piece they are referring to, right? And the third misconception is the language of the fraction. We may learn procedures that are efficient and make working with the fractions easier. For example, you know the rules of the division of fractions. So some students are saying in KFC, what does that mean? Keep, flip, and change? I don't know what that means, something like that. But that's really confusing if you don't know what that means. So a lot of times we are saying that divided by a fraction, you change that to multiplication and flip it over. Just giving the rule, that doesn't really make sense to me. How about to you? So here is one example from the textbook called No Problem. It's in chapter 3. So it's suggesting that 3/4 divided by 2 is equal to 1/2 times 3/4 or 3/4 times 1/2. So you are given, let's suppose this is cookie or whatever, and these pink parts show 3/4 of that one whole. If you are dividing this by 2 people, each person gets one piece, right? 1/4, and she gets 1/4, and you still have 1/4 left. So you can even break that, right? So this person gets another piece, but half of the 1/4, and this person gets half of the 1/4. So how much does each person get? Now we have to count these pieces. Now we just counted this part as 1/2 of 1/4. What's 1/2 of 1/4? That's 1/8. How many 1/8 there are for this person? Well, this is, this square is double of that. So two of these triangles make this square. So if this is 1/8, this will be 2/8. So total 3/8. How did we get that? That's same as 3/8. So you can do multiplication of 1/3 over 2/4. That's how this textbook explained. I like that, but that's not enough, I think. So here is another thing that I want you to consider. It's in division problem. So let's think back to the whole number instead of fractions. When we are doing the division of the whole number, we are doing how many 3's are there in 6? Well, 6 divided by 3 is 2, because 3 times 2 is 6, right? Using the fact family. Then we can consider the same thing by just applying this concept and extending it. So here's my question. How many 1/2s are in there in 3? I need to pause this video and consider how you can teach your student about how many halves are in 3. That's same as 3 divided by 1/2. Then think about that fact family. So 1/2 times that answer should be 3, right? How do we get that? Well, if you have 3, let's suppose these are the pizzas. Okay, so 1 whole pizza, 2 whole pizza, 3 whole pizzas. You have 3 pizzas there. Now you're breaking this into 1/2. So we have 2 1/2s in each of that pizza. Now, how many 1/2s are there in total? 1 1/2, 2 1/2, 3 1/2, 4 1/2, 5 1/2, 6 1/2. So we just figured it out. Oh, there are 6 1/2, right? There are 6 1/2. That now we can change this into multiplication. And what's the relationship there? That's the reciprocal of it. Now we can teach our students that, oh yeah, actually we can change this division to multiplication, and you can just flip it over by doing the reciprocal. Then you can use that understanding. Okay. The last misconception is this: which numbers are added or subtracted? So if we understand the role of the denominator again, then we are unlikely to run into problems with adding and subtracting fractions. However, we need to be aware that the students may run into problems when faced with different denominators. I already have talked about that earlier, right? So for example, 6/8 minus 1/4. And some students are doing 6 minus 1 is equal to 5. And 8 minus 4 is equal to 4. This misconception also will be resolved if the students understand the unit fraction. I already have talked about that earlier, right? So I want you guys to consider the unit fraction. Okay? Okay, so the misconceptions, all four misconceptions, we have talked about that. There should be some more misconceptions that you may face while you're teaching fractions. If we want to share anything, please do so. And if you have any comment about these misconceptions, please leave some comments in the forum too. Okay, this time I want to talk about different way of solving a problem. Once we have talked about Singapore math, and I think it is pretty useful to teach elementary school students for them to understand the fraction situation a little bit better, especially when they are given word problem. For example, Farmer Sally had 320 pumpkins to deliver. She delivered 3/5 of them to the first grocery store. On her way to the second grocery store, she dropped and smashed the 8 pumpkins. Oh no! After she delivered 2/3 of the good pumpkins to the second store, how many did she have left? Students already get panicked. Even some teachers can get panicked by looking at the situation, because there are more than one step to do this, right? You can always use the numbers, and again I say this, in solving mathematics problems there is not only one way. There should be some other ways that everybody can think differently, right? So one way that I want to introduce you today is using models. We call that bar model. Okay, so bar model is very useful to solve even for fraction here too. So let's consider this situation and represent that using bars. Farmer Sally had 320 pumpkins to deliver. So let's suppose that's one whole thing. So this one whole bar represents 320 pumpkins of Farmer Sally. Okay, 320. She delivered 3/5 of them. So how many equal parts are we making? 5 equal parts. 3, 4, 5. Let's suppose these are all equal parts. And 3/5 of them. So let me change the color. 3/5. 3/5 of them. Here, this shows 3/5, right? 1/5, 2/5, and 3/5. So total 3/5. 3/5 of them to the first grocery store. So this is delivered to the first grocery store. On her way to the second grocery store, she dropped and smashed the 8 pumpkins. So we can think about the ruined pumpkins are from these, right? So whatever that is, we need to take away that a many. And then after she delivered 2/3 of the good pumpkins to the second store, so whatever is left there, and you need to consider 2/3 of that. So we can draw another bar graph that represents this part. So let's do only the first part up to here first, okay? So we have 320 pumpkins, and if we are making that into 5 equal pieces, how many goes in each of these? We can do the division, yes. So 320 divided by 5. Then we can get to know how many goes in each of these boxes, right? So 300 divided by 5, we can do 5 times 6 is 30, and subtract that and get 20. 5 times 4 is 20, and the remainder is 0. So we know that 64 pumpkins go in each of these bibs. 64 and 64. Well, we get to know that 64 times 3 goes to the first grocery store, but we're not concerned about that, right? We are looking at the second grocery store, and we see that on the way to the second grocery store, so taking how many? This many, right? 64 and 64 together. That have to go to second grocery store, but she dropped 8 of them. So how many is left now? 64 plus 64 minus 8, which will be 128 minus 8, right? And 120 is only the good pumpkins. I'm sorry, not apples, because 8 are ruined. So there are only 120 pumpkins that were going to the second grocery store. But after she delivered 2/3 of the good pumpkins only, so we need to consider that 120 pumpkins here. So this is 120 pumpkins that were to deliver to the second grocery store. 2/3 of them. So we need to show that 2/3 of that, let's use this color, 2/3 of that should be this much part, right? This is 1/3, and that's another 1/3. So that's 2/3. 2/3 of the good pumpkins out of 120 pumpkins to the second store. Then how many is left? So we're gonna figure out how many goes in here, right? We get to know that 120 pumpkins are equally divided by 3, same sizes. So 120 divided by 3 will be 40. So each box shows 40 pumpkins. So how many pumpkins is left? 40 pumpkins is left. So I think the bar model is pretty useful. Consider solving this problem using different method than bar model. It's gonna be fun. Okay,